Okay, so thank you for the introduction. So this work is done in collaboration with Berkeley University and the ERI Robotic Lab in Barcelona, Spain. So what was the motivation of this work? Our goal was to design an efficient motion planner that's able to work in very complex problems that involve obstacles, differential constraints, but also uncertainties that can appear from the motion, the sensing, or partial feedback. So we're going to present the environment-guided RRTs that try to address all these problems. So as it's very difficult to address all these problems together, what we're going to do is first to focus on obstacles and differential constraints, and then we're going to see how to include uncertainties within our planner. So if you look at the general context of this work, most of the methods that work with differential constraints are using tree-based methods because they allow to incorporate the dynamic of the system by forward integration of these dynamics. So there is a lot of different work that's working on this tree-based approach. And many of them are using the RRT methods and these extensions, and this work is also a continuation of these extensions. So why using RRT? First, because it's very simple to implement. You've got these three main steps that are random sampling, search of a nearest neighbor, and expansion of the nearest neighbor toward the state. But maybe more important, you have this Voronoi exploration bias that has been presented previously, that really tends to have a greedy exploration strength, gives a greedy exploration strength of the planar. So RRT is really a good candidate for this kind of problems, but the problems that occur here is that the metric that's given doesn't provide always an accurate cost to go function because of the obstacles, but also the differential constraints. So what we can do to face this problem is really to try to find heuristics to improve the performance of RRT in these challenging situations where we have these problems. So what I'm going to do now is present two kinds of challenging situations and try to see how we can improve the methods on this challenging situation. So first kind of problem that can occur from obstacles when you're over-evaluating some of the states that's going to lead always to collision. So that's, for example, here the red state is illustrated here. That will always be extended, and they try to be extended, but they will lead to systematic collision. Whereas we would like to expand the green state that has lower Voronoi region. But now if you look in the literature, there is also a work that's called resolution complete RRT that propose to address this problem by basically decreasing the weight of the states that lead to collision and discarding the nodes according to their risk of collision using what they call the constraint violation frequency. So there is already some work that's proposed to address this problem. Now, a second kind of challenging situation may occur from dynamics, because the nearest node you're going to select cannot be really expanded toward the random sample you sampled. So that's again what's illustrated here. For example, in that case, you're going to select the red state, but it cannot go in the direction of the random sample, whereas we would prefer the green states that has better chance to reach the random sample. And again, in this kind of situation, looking in the literature, there's a really nice work that has been proposed, which is reachability guided RRT, which basically, instead of looking at the nearest node, will look at the nearest reachability set, what they call reachability set, that are these red or green regions that are the possible set regions reachable from a given state. So to sum up, you've got two methods from the literature that improve RT that really have complementary behavior, that really works, that are really helpful in some kind of situation, whereas the other is not in the situation. So what we propose here is just an hybrid planner that benefits from both types of heuristics that we integrate in a planner that we call environment-guided RT. So we propose a nice way to combine this method within a single algorithm. So it's really hybrid planner that combine all these two methods. So I will not go into details of the method, of the algorithm here. And we experiment, we evaluate the method experimentally. So until now I didn't speak about uncertainties. So here are the experimental setup we propose. I will not go into detail, but just to say we use the 4-dimensional state vehicle. And we tested on first experiment, which is a clutter environment where we can tune the difficulty of the environment in function of the size of the obstacles. And the key point here we have to retain is that so EG-RRT is more efficient than RRT, but also of all the other variants taken separately. But even more important, the benefit of the methods increase with the complexity of the scene. And we had the same kind of results in a maze-like environment where you can tune the difficulty of the scene in function of the narrow passage you introduce. Okay, so now we had a planner that works efficiently with obstacles and differential constraints, and we try to apply this problem with problems that also involve uncertainties. So what we propose to do here is to work in two steps. First, to assign a cost to the nuts of the tree we are growing, and then to guide the expression according to the cost of these nuts. So how to assign costs? So for assigning the cost, we're going to use LQGMP methods, and to guide the expression, we're going to use a principle from transition-based RT planner. So how to assign the cost using LQGMP? So LQGMP is a tool that allows to estimate the probability distributions over the states, combining Kalman filter and linear quadratic regulator. We use, in our case, this LQGMP to evaluate the probabilities over a restrict time horizon within our tree. And using a scaling of the environment and the standard deviation, we are able to estimate the risk of collision of the states. And finally, from this risk, we can compute a cost, give a cost to the nuts that's proportional to the risk of collisions of the path leading to these nuts. Once we've got these costs, we use the principle of transition-based RT to guide the search. So this transition-based RT is a tool that allows to explore low-cost region of a state space, of a cost space. And the key idea here is to add an additional test before inserting a new node that's based on the cost variation between two neighbor states, with has nice property to adaptively tune the difficulty of the exploration during the search in function of the difficulty. Okay, so we incorporate these things inside our environment-guided planner, and we test so in scenarios with uncertainties from motion and from the environment. So first environment is the clutter environment with light-like sensors. And just to sum up the results, we saw that using all these combined methods, we had a planner that provide more quickly a solution path which much more safer than using a standard RRT. So to give an idea, we skip from 8% probability of success with standard RRT to 87% of success in that case. We experimented finally in a clutter environment with 2 cameras. So here you have partial information about the environment with the orange camera that gives partial information about the x coordinate, and the green camera partial information about the y coordinate. So here again with standard RRT you've got 2% probability of success, but with EG-RRT you have up to 81% of success. So again, EG-RRT provides solution pass faster and with a safer probability of success. So to conclude this work, we proposed a variant of RRT able to work with kinodynamic systems with obstacles and uncertainties. It integrates within the same framework several prior work, and the very important point here is that all these methods are really necessary to address such complex problems. And finally, we demonstrate the method on challenging problems where we saw that it produces paths faster with lower probability of collision. And finally, as future work, we would like to pursue experiments on other dynamical systems and state space of higher dimension, analyze the safety guarantees we have respect to the solution paths found with EG-RRT, and try to see if we can locally optimize the solution paths found with this planner. So thank you very much. That concludes my talk.